2 people. Awesome. Thanks everyone for coming. This one is it's not going to follow the actual explicit course as well as the other one probably did, but I actually have a presentation this time, so it might be easier to follow. I'm calling this fantastic functions and how to fix them, because we're going to be covering kind of how to build a function again, just because we always forget, and then going into some other stuff. As per normal, it's the other Kevin, I see. As per normal, if you have it, a second screen is awesome. Otherwise, just follow along in R if you can. Because we're going to be doing we're going to kind of talk about some theory and then actually doing some practice problems, some kind of challenge questions. And one or two of them are pretty challenging. But I guess I have a question. Does everyone know what a linear regression is? Does everyone kind of use them in their stuff? If not, that's okay. Well, I just want to know if anyone uses it, because I do have one example that involves linear regression. So if we don't want to cover that, I can avoid it. But otherwise, we should be good to go. So let me know if you don't know really much about a linear regression, and I can kind of talk a bit more about it. But anyway, so just covering what I did last time. So remember, this is all kind of an extension of last time, just to remember and remind ourselves, what the heck is a function in R? How the heck do we define it? They're tricky. They're really hard to use. There's kind of 2 steps to every function. First, you got to define it in some step. So here, just what I've highlighted, we've got to define a function in some way. It always starts with the word function. That's how we start making our own function. And then it's got some kind of arguments. So these can be basically one thing. It can be many things. We can name them whatever we want, but we're going to have some kind of arguments we're using. I've got it in red here. Then we're going to do some manipulations on those arguments. So here, I'm just using the built-in exp function, which is like e to the exponent something. So it's like that constant value e. I think it's like 2.76 or something like that. Some value to the exponent of whatever our arguments is. So I've just added some random manipulation here. Doesn't have to be this, but I'm just exponentiating it. So that's why I'm calling it my exponentiator as the function name. So this part, we can call it whatever we want. I'm calling mine my exponentiator. And then finally, we're returning the output. So these are kind of like the main steps of every function. We got the arguments, the inputs, then we've got our manipulations in the middle, and then finally we want to return the outputs. And usually I like to call this out, but you can call it whatever you like. It doesn't have to be the out object. It's just that you just have to return something at the end, because otherwise your function won't do anything. So we can try this out in R. I'm just going to try copying mine. I actually haven't tested any of this in R, so we'll just see if this works. And you don't worry about running this too much just yet. I just want to see if it actually runs. So we've defined our function, and then we're going to try using my exponentiator. And on a value of like 5 or something. If we do that, we get 148.41, which I think is exp to the 5. Yeah, so it looks like it's working. So that's just a really, really simple function that we can fill in. And don't worry, I'll put the slides on Codar's GitHub after this, so you can get the slides from there, and you should be able to copy and paste the text as well if you're interested in copying it along. But for now, I just wanted to show you a really basic function. So hopefully everyone's kind of remembers this. So there's kind of 3 or 4 big steps: arguments, doing the manipulations inside the function, returning the outputs, and then finally we really want to just test our function. So once we've defined it, we want to just make sure it works. So we're just going to run it with a value inside of it. This is actually when we actually run the function. If we just do this part here, it will be defining the function, but it's not actually being used for anything. So it's not really super useful until we actually test it and really make sure it's working. Because often this part will run, we'll be able to define our function, but we'll often find when we try and use our function in the next step, that's where problems arise. And we'll talk about how to fix those problems in just a sec. With a fairly complicated function, I'll get you guys fixing it. Some other things that we can do with this. So a few more more crazy things. So here I've just basically we've taken our function, and instead of arguments, we filled in a new kind of arguments. So we've got inputs, and we've got a multiplier argument that we've added. So we can have 2 or more arguments. We just have to be comma separated with them. And so now, and they're actually named, and they have a default value. So defaults just means I can set this equals, so inputs equals 5. That means that the first input is going to be basically 5 unless we tell it to be something else. So the default is going to be 5 unless we change it when we run it later. And then we've got this multiplier argument. So now we're taking our, oops, I've actually made a mistake here. Oops. It's supposed to be, the comment's supposed to be outside of that. Oh, what's going on? Oh, something's weird with my computer. I think it's just a problem with me sharing screen. It's doing something really weird. Anyway, we'll just delete that for now. We've got our we're exponentiating or doing an exponent, then we're multiplying by the multiplier, which are just, again, we're just making this up, but a function for you can be like anything. So you can do anything you want with this function. So it's really useful. And then finally, we're returning an output as out2. And so we can see when we do this, we can run it with inputs equals 5, multiplier equals 100. We could change these values to whatever we want. So it can be like 101. Oh, my computer's doing weird things. I think I'm in like insert mode. Anyway, I'm going to try not to type text too much. So anyway, we can change these values to whatever we want. And basically it's fine. And we can even run this function without writing the argument names. So as long as they're in the correct order, we can write 5 as the input, 100 is the multiplier. We don't need to have the actual names of the functions in here. So I think this is something really important that for beginners, it's often forgotten. Like as long as we put them in the same order as our function says they are, then we don't have to put the argument names. We don't have to write them. Sometimes it's better to be safe than sorry and just write the argument names though. All right, so that was kind of argument naming and defaults. Again, I think we've done a bit of this. So does anyone have any questions about this stuff before I move on to maybe a challenge? This is all easy to like listen, but it's a lot harder to put into practice. So we can do this part together. Sorry, my door. All right, so here's a little challenge question. Why don't you make? I don't have the time. I did this in the hour before this. I don't have the time to learn how to do it. All right, so we've got a little challenge here to try and do. It's gonna be a little bit of time on this. So the object of this challenge, and I made this challenge hopefully somewhat useful to people because we all do kind of simple linear regressions, and sometimes it's good to have some way of using that data and automatically like basically running with it, like using that results and giving yourself an output that you can put in a report or something. So we're going to try and make a function that basically just takes as input a simple linear regression model object. So mod 1 in this case is kind of like what I'm talking about. It's a model object. It's whenever we want to run a linear model in R, it's going to save it as a model object, and we can name it whatever we want. But we're going to take this model object and we want it. If we actually look at what this does in R, actually, I'll just show you. I'll just copy this part. Maybe I'll paste it in here so you guys can try it yourself. Basically what this does if we take it to R is if we run this, we'll have this model object, and this model object is okay, but it's a little bit hard to interpret sometimes. So if we look at it, it's kind of got all this jargon, which we might, it's not really ready for like a paper or anything. So we might want to like spice this up. Might just want to like write it in terms of like a linear formula that we would normally want anyway. So what we really want is we want to take this intercept and this slope and write it out kind of as a formula, like y by a plus b, or however you learn the mx plus b kind of slope formula. So we just want to change kind of the model object to something more useful for us. So we're going to write a function to do this, where we're going to take the model object, and we're going to change it. We're going to do something with it. So just going back to this. So what we want really is we want something like this. It doesn't have to be exactly this. You can customize it how you want. We want it to return basically a statement like this, where it just gives us the fitted relationship. It gives us y by the intercept plus the slope, or Australians always have a different way. They're taught not slope. It's a different word. My students are always telling me this, so I shouldn't use slope, but hopefully everyone understands what I mean by slope. I always forget what they teach people straight out of high school, but it's different from slope. Anyway, you get the idea. Gradient, yes, thank you, gradient. So yes, so we want to use the intercept, and we want to return the gradient, and then we want just like times x or something like that. So let's try and do this as a group, or maybe we'll just start off writing a part of the function, and then I'll let you guys try and do it as yourselves. But just a hint, the coefficient function, this is a function that returns coefficients from model objects, and paste. which is a way of joining together character strings, or basically it can join like character strings with numbers really easily to make a statement like this. They're going to be super helpful in our function to make this work. All right, so and then in bonus points, we won't do this as a group, but if you can return a significance like asterisks at the end, if the slope is significant, that's even better. But I'll leave that to the pros to do. I'm not going to cover that too much. So let's give it a go. Maybe I'll try and have this open in some way. Hopefully everyone's got the challenge down now. So we're taking a model object and we want it to return some kind of like statement about our relationship that we've formed. Hopefully everyone's kind of got this. So how do we start? Where do we start with this kind of crazy function that I've invented? Well, the first thing we got to do is, or the first thing I recommend doing is naming the function and just writing out what we're going to need in the function. So to start off, so challenge 1, let's just start off writing the basic function code, which actually we can just copy what I have above. I'll just copy this and I'll paste it down here, and we can fill it in differently. So we're not going to be doing exponentiating or anything like that. We're going to need a different name for it. So does anyone have any different name we can use for this function that we're going to write? So we can name it whatever we want, but does anyone have any recommendations? Steve? No, I need more. I need a better, more descriptive name than that. What about, I don't know. So we're trying to make like a significant statement here. Let's maybe call it something like sig state or something. Sig statement or something like that. So that was, it's more descriptive than Steve, unfortunately. Sorry, Kevin. I'm not going to go with Steve in this case. But yes, you could name it Steve if you really want. It just might be hard to remember after a while. There's a whole like page, I think, on Twitter about like people naming their functions different things slowly over time, and eventually the function name makes like no sense to anyone, and then they find their old code, and it's hilarious. I've seen it on Twitter many times. So we want to avoid that by making something super descriptive and not change it too much. Okay, so we've got significant statement as our function name. Then we're not going to be doing this kind of thing. We're going to have something with our manipulations here, but for now, don't know. Here, I'll just copy this in case anyone wants to use this backbone for their own stuff. All right. So what kind of inputs do we want? Or maybe we want to call our argument something different. So our input or our argument is going to basically have to at least be this model object, right? So we're going to want in a model object. So maybe I'll call this just mod object or mod obj. You'll often see object written as obj. So we can do mod obj as kind of our input. And if this is going to be our input instead of arguments, we'll just replace it throughout everywhere. So mod obj will go here and here. All right, so now here's what I'm going to try and get you guys to do more of this. So now we've got it reading in. What's one way we can get out the coefficients from this model object that's going in? What's a way we can do that? Does anyone have any ideas? How can we pull out the model object, the coefficients from this model object using linear regression? We can even try it on this mod 1. Okay, let's do it. Model object. I try and keep my code like super short names, but I think it confuses other people, so I agree. Let's do it longer name, model object instead. I agree with you, Legana. So how are we gonna do this? Well, I did mention before, we can use this coef function. That might come in handy. So when we think about this mod 1, if we try, because this mod 1, we've already defined it above. This one actually exists. This one, in this case, if we try running it, it won't exist. But this mod 1, it does exist. So we can try it just on this, just try and troubleshooting. So for instance, mod 1, if we do coefficient of mod 1, what we get out of it is we get, this is basically like a vector. It's got 2 numbers in it. It's got the intercept as 1 and the slope as the other one. If we just want the intercept, we can do a subset, it's called, where it's called, you use square brackets and you write 1 means give us the first value in this vector. And that will give us, in this case, the intercept. So this returns the intercept. And then similarly, if we want to return the slope, just copy paste that, change this to a 2. Now it's returning just the slope. And it's got a name above it, but that actually doesn't mean anything. So don't worry about this intercept and weight or WT. That's just part of the original data set. So it's just a name on the actual vector. It doesn't actually mean anything. All right, so we've got a way of returning these two things. That's like one big part of it. So we've got a way of returning the values here. So I can put this in here, and maybe I can actually name like intercept as that, and I can name slope as this. And now I've got a way of running it. But what's one thing that I just did that is going to introduce some problems in my model? What can anyone see what I just did? Specifically with this part, what have I done that's going to be an issue in this function in this case? Remember that the function needs to be adaptable to any model object. So when model object changes, this part has to change as well. Any ideas? There's something that I've just done that is kind of going to screw me up later if I try and run this. Yeah, so there's a naming issue specifically with this mod1. So remember that mod1, that's defined outside of the function right now. So what we really want is we want it to be kind of versatile. So we want this input model object to actually be wherever mod1 is. Otherwise, it's just going to use the same model every single time. It's never going to change. So we really want it the one thing to always check with is that we're always using the argument name. And I'll show a way of doing that right after we're done building the model, how we can check that. But for now, that's perfect. So we got intercept slope going in. Okay, so we got intercept slope going in. Now we need to make a statement of some kind, like we have over here. So we need to make it like a fitted relationship. I'm actually just going to copy this because I'm lazy and paste it here. So we want something like that, what I just put in the chat. And that's kind of going to be our output in this case. So we want our out to be something like this. Oh, we copied with, just note that the quotations, when I copy them in, they're not real quotations for some reason. So I just have to delete them and change them again. So your code should highlight differently with the quotations. So be careful if you copy what I just pasted in. It doesn't quote, so you might have to replace the quotation marks again. We want something like this. And one way to do that is using paste. So the way paste works, for instance, we use paste and we return like coefficient mod 1, comma, coefficient mod with the second one. It will just write them in, right? It just writes in these big numbers. And we can even add extra things in between with more commas. We can actually add quotation, comma, space, quotation. We'll add it so that now it's like a number with a comma and then another number. So we're getting there. So now we can keep going from here. We can add a little bit more. One annoying thing is the numbers are printing the whole number, which is really annoying. It looks ugly. So we can use a function called round on that. If we use round, and I think round has a default, which is, it's a way of rounding numbers really easily. Round has a default of 0 digits. So maybe we want digits equals 2 or something like that. So we've got, that's looking better. Maybe we just want digits equals 1 actually. So I'll do that for, that's kind of like the, I'm kind of working inside and outside of the function. So maybe I'll just go inside the function now. And we'll try doing this as a kind of a paste statement. So we'll go paste, and then we're going to round off the number. Paste, round off. The first number will be the intercept. So we can take the intercept here, paste that in, and we want digits equals 1 or something like that. It's up to you, but you can call it however you want. So we can't run this because we don't have an intercept object, but what if we just define intercept outside of the function? So one way you can start, when you start building functions, it's kind of nice to just test it and make sure everything's working. It's harder to build a function perfectly and then run it good the first time. So what I like to do is I just, outside of this function, I'm gonna actually define these things inside that are working inside the function so that we can play with them. So I'm gonna define intercept and slope outside of the function. That way, and then these run because we're using mod 1, which is, again, it's outside of the function. So these are good to go. So now when we go inside the function, we can actually run intercept and it's got a value in it. So now when we're using our function, it's actually going to be useful and easily run with that. We can try rounding. Okay, so that looks good. So we've got intercept 37.3. And then we're going to add, there's going to be a plus in between. So we'll just add a plus. And then we'll add the slope, which is the same, but this is just slope, comma, and then we'll add more quotations times x in this case. That's how we get this little bit at the end. And we'll just test how this is looking so far. 37.3 plus minus 5.3 times x. That looks good. Now let's just add the first part of this, which is just this. Copy that. Add a comma and quotations. And then finally, we've got this kind of fitted relationship where we're actually writing it out as it is. The last thing to do is we just have to save this as out. So out into here. We can get rid of this one. And now it should hopefully return out okay. All right. So I'm going to try and evaluate this whole function now and see how it works. I'll evaluate it. By evaluate, I mean, sorry, define it. So I've defined this function. I've got this big long thing that just basically is how I make the significant statement from it. And now we can try running it sig statement on mod 1 in this case. We could run this and there you go. It produces the fitted relationship. And if you don't believe me, we can try running a different model. This maybe with the mtcars data set. Maybe I'll run, I don't remember all the names of this data set. We can try using disp as well. So maybe I'll do mod 2 using, instead of weight, we'll use displacement or disp and try running mod 2. And there we go. We got a fitted relationship. It's very non-significant. So it's basically 0 there. So clearly we picked a slope that isn't very significant. But we can print out now this other relationship as well. So this significant statement function is completely versatile and we can apply it to anything. So it's, I think that in this way, you can quickly see how functions are awesome because you can build whatever you want with this. I'll just copy this just so you have how I've done it. Just note that the quotations will be messed up if you try and paste it yourself. But yeah, so that's it's simple yet complicated because we're doing a lot of stuff in it, but a way of just printing a significant statement with the function. All right, does anyone have any questions about that? Sorry, it's not like the most easy exercise to just get you to do yourself, but there will be a few that are a lot easier to try yourself in the next little bit. That was kind of our big challenge of the day. Does anyone have any questions about that or any feature recommendations? As in, we could add more to this function. We could always add a little bit more to make it do even cooler things. And I think we will in the next little bit. And I'm aware that functions aren't the most interesting topics, but there will be at least one cool thing I think that everyone might learn in the following slides to come, not quite this one. But anyway, we talked a bit about it last time, function control. So what happens if we get the wrong inputs? We put in the wrong arguments and we don't want it to continue anymore if we got the wrong arguments. We basically don't want our function running until it hits some weird error and it gives us this really vague and opaque message. So often what we want to do at the start of our function is just check inputs. Especially this is the case when you've got a really complicated function that you use often and that you might be sending to someone else. You might add these in just to make sure that they use your function correctly. So a few of them that you can use is the stop if not function. So we can add it, and basically this is just saying is numeric. If we look from the inside out, is numeric is checking, is the argument a numeric value? If it is, then it returns true. If it's not, then it's a false. And then the next thing, this exclamation mark, we talked a bit about last time, it inverts whatever we said. So if basically this is saying, is the arguments not numeric? This part in here, because we got this exclamation mark that inverts the logical. So we're saying, are the arguments not numeric? Because we want them to be numeric, but if they're not, then we want it to stop. So that's what this part is doing here. So we can try to stop if not, and we can also use this if statement. It's basically almost the same. We can check if it's something, and then we can write stop with our own error message if we like at the end. So for instance, is it a data frame? If it's a data frame, it's too big for our function, it won't work. So we got to stop it right away with that as well. So that's function control. I think we talked a bit about last time. You can try it out here with this 5 in quotation marks should give you an error. So we can try this really quickly with our function. I thought I was going to do a challenge. So all we have to do is just literally just go in here and maybe paste this in. Maybe I can't paste this in. Well, I'll just write it out. I'll try stop. Oops. Stop if not. And here's where we might want to just make sure that it's a model object. So for instance, if we want to check what a model object looks like, we can go is on mod 1. And it'll say, oh, it's a linear model. So I think we can say, is model equal to linear model. So we can do something like this to make it work for us. Don't worry too much about knowing this, but we can basically use any as a way of just checking to see if any of multiple logicals is true. So we're checking to see is any part of this linear model, or is this model at all a linear model? And of course it is a linear model. And then any just means that if there's one true, it'll return true. And then finally, we can add an exclamation mark. So if it's not that, so it's a little bit confusing, but basically this is going to stop if it's not a linear model. Last thing to do. We'll see if this works. I might have screwed it up. Oh, I think I did it maybe the wrong way. Yes, okay, that's better. Sorry, I didn't need the exclamation mark. So really complicated way of just saying, basically, is this a linear model? And if it's not, stop the function. So stop if not just says, okay, is this true? If it's not true, we're going to stop the whole thing. So I can define this, and it's basically now going to only work for linear models. So here we got a linear model, it works, but I could try the same thing on, let's put this in quotes. And now it can't find mod 2. It thinks it's a character string. So it's going to be, oh, that's not working for us. And it's going to stop. So it's a really, really simple way of basically making our model work better, or making this function work better. All right. Boring. Now this is the part where I think everyone might learn something. Maybe not though. Probably not actually. Everyone's too good now. But there's a thing called function scope. And basically what it means is that inside your function, unless you return it at the end, you can't get out this other things inside your function. So for instance, remember before where I did like an exponent. So e to the power of whatever my argument is, and then I did a multiplier times 100 or something like that. Well, what if I just wanted both out1 and out2? I wanted the exponent part, and I wanted it to return when it's also multiplied by 100. So I want basically out1 to return, and I want out2. We can't just write, it's not as simple as writing out1, comma, out2. That actually won't work. It won't like it. It will not be happy with us. So we can't actually write it like that. So we have to find a different way of getting out these objects, out1 and out2. So maybe we've got multiple things we're doing in our function. We want it to give us everything out. And this especially is true for some of the stuff I do. I'm always have many different outputs from all my models. So it gets really complicated. And I need to just give me all my outputs separately. And they're not at all the same data type. There's some that are matrices, there's some that are data frames, there's some that are like lists and things. So I need to stick them all together and get them out. So one way you can do this, and this is the bad way, is using a fun operator called the double arrow sign. And I learned really quickly in my undergrad course that you can do this, or I was doing a project actually for a professor, and he found out I was using this, and he got really mad at me, and I didn't know why it was so bad at the time, because I wasn't a programmer. But basically, if you use this double arrow sign in your function, it will define that object globally. What that means is it'll take that out1 and it'll exist now in the real world. It'll take it out of the function. Now out1 is like, I'm a real boy. It's invented out1 out of the function. And in that way, it's kind of dangerous because it can override things that are outside of your function when you run it, which is scary. It's kind of not a good behavior to have. So that's why people don't like it, because it's not tractable. It's not coming out of this. When you run my exponentiator, if you run this now, it's just going to give us the value of out2. But without knowing it, it's also in our environment created this out1 object on its own, like completely by itself. It's not attached to anything. So it's kind of scary. It's this zombie object that's created. So you can use this double operator to get this out1 object and the out2 output, but it's dangerous. And I guess I can show you if you're so interested how it's really weird. So look at my my environment. There's no out1 object so far. Let's see if I've written this function at all correctly. So if we define a function, and now we try going my exponentiator 5, maybe I'll save it as x, just save it as a value. Oops, and I've got this weird, oh, and I'm sorry, I'm missing something. It didn't copy this part, all of it. Out2 is equal to out1 times 100. I don't know why I didn't copy that. Anyway, redefine that, try running it. Now look, I've got x, which is the value of out2. It's whatever it was times 100. But look at my environment. I've got this out1 object that's appeared. if I rerun this again, so maybe I run it with a value of 1, all of a sudden out1 also changes. It just overrided the previous value of out1, but it's not even coming out of my function. It's just happening over here. So you barely even see it happening. So that's why these are really dangerous in terms of coding. Obviously, it's what you define as dangerous. For most people, it's not dangerous at all. It's not scary at all, but it is changing things that you might not intend it to change. So you got to watch out. This double arrow operator is kind of scary. And I was tricked into using it for a while, and it's actually really bad. The better way of doing it, so if you want to get out1 and out2 out, the best way to do it, shame, is to actually just make a list object. And it's kind of annoying and it's kind of cumbersome, but you can list objects, if you remember from, I think, Jacob's lecture on it, they can contain whatever you want. They can have data frames, matrices, more list objects in them. They're basically, a list is like, you can have everything you want inside a list. And you can even name them. So you can name them exp equals for out1 and exp times 100 for my out2 value. This way now, when I get out this out3, this third final output, I can now call it using the $sign. So if I try running, if I just change this now, delete that, and now I just add out3, it's a list. I can name it whatever I want. Like I can call it like first output equals out1, second output equals out2, and then finally we're going to return out3. Now when I run this, X kind of looks weird. This is what kind of a list output looks like, but now I can actually call certain things like X $sign first output will give me just out1's value, what was in out1, and same thing with the second output. Now I've got multiple things coming out of my function, that my super complicated function that's doing so much, not really, I can now get multiple things out of it. But the important thing is that I've added them as a list, and I haven't used that double arrow sign because it's a dangerous thing in coding. And yeah, if you ever wrote like a package in CRAN or anything and you had double arrow signs, I think they'd immediately remove you from CRAN. You were not allowed to use that kind of stuff when you're doing really advanced programming stuff, because it is a bit dangerous. It'll delete things that you don't mean for it to override. All right, so that's how we do function scope in R when we want multiple outputs. So now I've got a challenge that you all can complete. Using that, hopefully we've still got it somewhere, using that significant statement function we had before, it doesn't have to be the same as mine, but hopefully it runs previously. Try and add so that you get back basically some kind of $sign, some kind of list object that returns both the relationship value, which is like what our statement, our significant statement on the relationship, and it can also return the slope and the intercept by themselves. So often we want this nice thing of describing the relationship, but we also want the actual values of the slope and the intercept in case we need to use them later. And we want them as numeric. So this is a character string, which we were returning before. Now try and change this so that out not only is this big long statement, but it also includes the intercept and the slope as well. So we want to make a list object that includes those three things. We've got the significant statement, the slope, and the intercept values all separately in a list object. So that's my challenge if anyone wants to try it. I'll paste this here again. Oh, and I see someone tuned in, so everyone definitely might not have it. Just note again that when you paste this in from Zoom, it adds the weird quotation mark. So if I paste this in again, I think it actually worked okay this time. So maybe hopefully it works okay if you paste that in as it is. So again, just to remind you, the challenge is try and add multiple outputs for this function that we've already built. And I'll just give you a few minutes to try that for yourselves. We'll pick up in maybe 2 minutes if you can, but if you need more time, we can wait. So if anyone, let me know in the chat if you've been able to do it, or if, let me know if you're not attempting it, and we can move on. Anyone still working on it? Want me to pause or no? Envision the way I would do it is using this list way. Hopefully you didn't use the double arrow way, to get out both significant statement we had before, slope and the intercept. We're going to put them as a list object. That's how I would do it at least. So like one thing we can do, for instance, is take this part and move it to a new thing, like a sig statement, or maybe we'll call this relationship, because we've already used that name. So we've got kind of intercept, slope, and we've got the fitted relationship, or like the statement we had before, we're just calling it relationship here. And the last thing to do is just make this a list object, right? So we can go intercept, slope, and relationship. Try running this. Now, when we run it, we're going to get out 3 outputs. We're going to get the intercept, the slope, and the relationship. One thing that we want, though, is we probably want it named. So to name it, we can literally just copy and paste it as intercept equals intercept, slope equals slope, and relationship equals relationship. Or maybe we want to call it significant statement here. Significant statement. Now it's a named output. Now we've got intercept coming out as intercept, slope as slope, significant statement as this fitted relationship. All right. So that's how we can name the output. 3 different outputs we're producing now. The function. All right. So that was that challenge. And then lastly, which I think is the most important part of making functions, what is the best way to fix a function that was broken? So here I've just got a function that I can tell you right now, I don't think it's going to work. I haven't run it in R, but I'm pretty sure it's not going to work, hopefully. If it does work, I'll eat my words. But we know we've inherited a function from someone. We don't know where the error is. Where the heck do we start? Do we just rebuild the function ourselves? We don't even know what this function is doing, but trust me, I think we can solve it. And there's, in my opinion, a really easy way to figure out where an issue is happening in a function. So I'm just going to copy this. I'll just paste it into R quick, and I'll give you a code as soon as I get it formatted properly. I'll remove the weird spaces that it adds for some reason, and now I can give this to you guys. So we got this function, and there's a problem with it. There's an error somewhere inside of it, I think. Let me try running it. So it evaluates okay, but if we try and run rand loop, and we could just run it with the defaults by just putting it blank, that will make iteration equals 100, n equals 10, and mu, whatever that is, equals 5. If we just run it with the defaults, object n sims not found. Oops, I think I actually already made 2 mistakes with it. Sorry. This should be n. so right away, this is one helpful hint right here. It says object n sims not found. And clearly in the arguments, there's no n sims. So I made a mistake right here where basically this n sims should actually be n, because I changed it, I think, at one point to n, and I didn't change it back. So let's try rerunning this again. Rand loop, sorry. And we can rerun it, and it's working. Oh no, it wasn't supposed to work. Well, interesting that works. I'm really surprised by that. Anyway, let's say I go back to where it was broken before, where it said in sims. So what I pasted before, I don't know how it's working. I thought I designed that well. Clearly you shouldn't make presentations too late at night. Or I'm too good at coding, clearly. Just kidding. So we've got this function, and here I just changed it back so it doesn't work. And we've got ran loop now, and it doesn't work. It says object n sims not found. Imagine we didn't know where n sims was. We had no idea what anything was. So we wanted to investigate how to fix this function. I always recommend the best way to do this is to just copy what's in the arguments, copy them, paste them outside. Because remember before we were using arguments that were inside the function and we paste them outside. And I just, if you want to run them all together, you can change the commas to semicolons. And now if we run this, we've evaluated iteration has a value, n has a value, and mu has a value now. Now what we can do is just comment off the beginning. So if we just add a comment on the beginning of the function and the end of the function, now we can actually run everything inside the function as it is, and we can really test where it's going wrong. So again, starting from the start, we basically run this so that we have our arguments. They're in R, they exist. The next thing we do is we can run it line by line now to see exactly where the function is. So we can run the first line, that worked. Second line, there we go. There's an error in this for loop somewhere. So even though we don't have any idea what this function is doing, we can now run it line by line. We get an error in the for loop. So the next thing we can do with this for loop is check the first iteration. So since the for loop is using I, one easy way to do this is just to write I equals 1, start it at the first value. So it's going to go from 1 to iterations. It's going to go from 1 to 100, but we'll just start it at I equals 1 and see if this is working. On values, oh, there we go. So here's where our error is happening. So exactly at this line, when we run this line, we get an error message, and it's saying object n sims not found. So that's where you'd be like, well, where does n sims come from? Oh, it was misnamed. It was supposed to be n. There we go. So if I run this, now it's working okay. And I can look at the values inside. Basically what this function is doing is just drawing random values from a normal distribution, and then it's calculating the mean of them. So next it's doing the mean, and it's saving them into out I minus 1. Now one thing that I was surprised that it worked is that I forgot that if we try and save null as something, it'll just not work. It'll run fine. So if I run this, it runs, but if I actually look inside out of I minus 1, it doesn't exist. And the reason why it doesn't exist is because right now I is set to 1, so 1 minus 1 is 0. And so if we're doing a subset of 0, basically we're returning nothing from it. So actually, the real mistake I tried to add to this is that the minus 1 was screwing it up. What I really want is I want out to be saved at the ith value. So here now, if I run this, out is now saved as 4.79, and everything else should run. So I just wanted to delete that minus 1. All right, and from there, this for loop should all run and return output. Since it's not a function, it doesn't work, but we can look at the outs itself like that, and then we're good to go. And the last thing we have to do to put it all back together is we just delete the comments, and now our function should run properly. So if we do the ran loop, it's giving us basically the mean value, 100 different simulations of the mean value from a normal distribution is what this function is doing. All right, so the trick for debugging, really the steps for debugging, just going back to this code, is simply, just go down. You define the function's arguments outside of the function. So we take out those function arguments, we copy them, we paste them outside, we put semicolons around them so that we can run them all at once. So instead of commas, because if you try and run it with commas, like if I just did this, copy, paste that, it doesn't like commas. So we just replace them with semicolons, which you can quickly do with Control F if you've got a lot of arguments. And then finally, we just comment off the beginning and the end of the function. Or if you're really careful, you can just not comment it off and just highlight specifically each things. But now we're running each line by line in the function, and somewhere we'll get an error message if the function's breaking. So using this method, basically we define our function arguments and then running it line by line within the function. It's a really quick and easy way of finding exactly where in your function your code is broken. And to use this as an example, I'm now going to, and I haven't practiced this, but I'm now going to attempt to get you guys to debug my entire thesis model code. So we'll see if this works. I'm just going to load a bunch of preset functions that should work okay in packages. Once this is done, I can do the next thing. Of course, I'm running it while sharing my screen, so everything might not work properly. We'll see. This is where I truly test if I've coded it properly. Now I've got this function run IPM. It's called an integral projection model. It's basically all I do for my thesis. And just to put it short, it's like a really, really big model. I'm also going to need this stuff. I've got everything kind of loaded here. And now we can actually run a simulation with this. We try running it. And everything looked okay until it gets to level density. Actually, I think something else has gone wrong. Oh, so this might not work at all. We'll see if it's running. I think I've had a different error in my model, but let's try and debug it. So this is basically how I debug my code throughout. So I've got this huge, massive function called run IPM. That's what's basically doing my whole model for it. It's got a ton of initial inputs that only I understand, so don't worry about knowing what they are, but I will try and debug it ourselves. But what I do is I've got basically all the inputs or arguments commented off up here, but I can quickly uncomment them. And to basically debug it, I just run all these arguments. So that runs okay. And now what it can do is I can skip this beginning part. So again, I'll comment it off. And now I can basically run it line by line. But in this case, I've got huge sections kind of that I can run it section by section. So the first part is just initialization. The next part is setting a few more things to initialize the model. And then we're running through years. And this is supposed to be a coral reef. And the coral reef is supposed to be alive, but currently it's not. So now in this for loop, this is probably where the problem might be happening, but I just try running this for loop. We'll see if it runs okay. So far, so good. This might actually have caused an error, we'll see. So it's running through time and it finished running. So that means the for loop is okay, or sorry, the for loop through time is okay. So lastly, we get to saving outputs. And oh, there's an error. So I'm finding object X not found. So, oh shoot. Yeah, I changed the name of that. My bad. So that was actually an error on my part. Didn't mean to have that in the inputs list. I didn't actually have anything called X. So I'll just delete that. I changed it to NX and I forgot to delete that part. Try running inputs, outputs, and then all these other outputs. I've got a bunch of outputs, as you can see. And then lastly, I save it all as out. A big long list of many different data frames, and then I actually make it say complete at the end of the function and return out at the very end. So now I think I've fixed it. I think I changed that. I deleted that thing that was not running. I'll just uncomment this off. So now and then redefine the whole function. So I'm just running the whole function again, redefining it. And now hopefully it probably won't work just because my luck is against me today. But now hopefully as you can see, using this method, you can kind of quickly figure out where the bug was happening. And obviously it was a practiced example, but let's hope that this runs now. There we go. Okay, it ran, thank God. And now we can see our simulation where the population dies, I'm pretty sure. There we go, there's my simulation. I've already got a pre-built-in graph for this, but anyway, you can see it's running finally. This is like all I do though, so it's like, that's the boring part. It's not very interesting. So anyway, you can see how basically the reason why I keep all this stuff up here is so that I can quickly debug it. I can quickly add in all the inputs so then I can run line by line inside my function. If I didn't have this, I would basically have to evaluate my function, see if it works. When it doesn't work, go back again, evaluate my function. It would take forever. So I just leave this here to quickly just basically uncomment this off, run all my arguments inside of it, and then I can now go inside my function and run things inside my function and see how it works. So that's why I keep this here. I think that's the power of this kind of debugging technique. So the main point I guess I'm just trying to make is just that this method, at least for me, has really been helpful. Just taking out your function arguments, pasting them, adding semicolons, running it, and then now you can run line by line throughout your whole function and figure out exactly where the error is occurring. And from there, it's really easy to debug usually. You can see, oh, I just forgot to define that thing. So that's my tricks for fixing functions. I think the challenge question was just fix my model. Yeah, so I think that's it. Oh, and then saving outputs. So really quickly, we want to save outputs. We can run, like, for instance, this random loop thing that I had before. This random loop function, we can run it 1,000 times, save it as X. Oops, I might have accidentally deleted it. There we go, save it as X. And now I want to save this. Let's say it was a simulation that I want to save. The easy way to save it in R that I like is writing save, your object name, X, and then you just write where the file you want it to save is. File equals, and then I'm going to call it my like X results dot R data. So that you have to add this little n to it, dot R data. But basically it's going to save it. And right now it's going to save it wherever my working directory is. So if you remember, if we go session set working directory, we can set it wherever we want, choose directory. So I might want to save it to my downloads, for instance. I'll go to my downloads folder, save it there. And now when I run this, it's going to save the file, and I can go to my downloads, and you can see that it's now saved in there. I have thousands of things in my downloads file, but here's my X results. That's my R data set. So one way I can open it really easily is I can double click this, and I'll actually open, it says, do you want to load this data? And I'll go, yes. And it will load in, and it's going to load in exactly how you saved it. So it's going to load in as X. So now we get X back. And another way you can load it, so let's try removing X now. We'll delete X. Another way you can load it is just using load. And here you just write file equals, and you just write again the same file name you had saved as. So I'll just copy this, paste it here. Load file X. And now you can see in my environment somewhere, X, here it is. X is there. I've reloaded it up again. So that's one way to save your R data, your big tables data. You can save it as .r data. You can save this as a CSV. It's just write.csv. And I think it's just the same. So you write X file equals X results.csv now. There you go. It's written as a CSV, and similarly, you can load it basically the same. It's right there in my downloads folder. Everything's good to go with that. And yeah, so that's basically the main way I save R objects. I'll include these slides, but I'm pretty much out of time. But there's also this RDS way. The only difference for these .rds files compared to RData, oops, that's actually a mistake, RDS, is you save RDS and read RDS. And the main advantage of that is that you can actually define it as like a new object name. Whereas when you're using RData, whatever you saved it as, like the object name beforehand, ran results in this case, when it loads it, it'll keep that name. So it's kind of annoying because sometimes it'll override things if you have too many things. Sometimes it's better just to use this RDS format, but really they're basically, I think they're fairly similar in terms of like computation size and everything. Or CSV file, again, is also good. I know those works, but there's kind of many ways of saving data. If anyone has any specific ways I can try them, but that's pretty much it for me on functions. Sorry, it's been a kind of a whiz and not nearly as much. And if you like, you can try this challenge question, saving and loading the mtcars dataset, which is built in. So you can try doing that yourself if you like. mtcars is just about miles per gallon and things on a bunch of different car brands and models. But anyway, that's it for me for this kind of advanced functions presentation. Hopefully you took away something. Don't worry if you didn't. Functions are hard, very hard. It took me forever to get into them. Once you get into them though, you kind of go crazy and you build giant functions like I do, and no one else understands them, and hopefully you will document them enough that you can find them and understand them yourself. But yeah, another thing I didn't really talk about in functions is that, again, it is really good to comment on things. You can see here, I didn't really do a lot of commenting. And in my SC202 course I tutor, I would have probably failed the assignment because I didn't comment enough. So always comment more. Like here I'm doing multiply by 100, just simple things just so you remember. This is save outputs as a named list. Always adding comments to explain what you're doing, super helpful for you and for everyone else reading your code. All right. With that, that's it from me. Does anyone have any questions about anything? So we've done a lot already. We've done functions in R, arguments. We did challenge question. We did function control, function scope, and what not to do with function scope. And then finally, how to fix a function the easy way. And saving outputs. Otherwise, thanks for listening. Or maybe add a general comment. Yeah, Totally. If you're giving it to someone else, definitely always do as Legana says and add as many descriptions and comments as you can. Oh, and sorry, and I missed Lorenzo as well. Yeah, and Lorenzo, the same thing. Yeah, exactly. It depends on who you're giving it to, right? Like if it's just for you, I often just don't do that as much. I know what the outputs are, and I try and name the outputs and inputs. Pretty easy things to remember, but yeah, it's always good to have more description rather than less, especially when you're not going to touch the code for a while.